acetal. Because two bonds don't like this. What's unique about sucrose is that, remember, acetals are usually made by one sugar acting as an alcohol and the other sugar acting as a hemiacetal. Together they make an acetal. The alcohol is one of these sugars that makes the acetal is also the hydroxyl group, the anomeric center. This anomeric center and this anomeric center end up being acetals. If you treat this with acid, acid can tear apart acetal groups sooner or later. And this is clearly a disaccharide. One sugar and the other sugar. This sugar is D-glucose. This sugar is D-fructose. You add acid and water. This can go from the top to the bottom, back and forth as it opens up. Create a mixture of alpha and beta. D-glucose. And from this piece you get another sugar whose name you should recognize and remember the structure. That's fructose. Those are the two sugars that were isolated this century before. And this is the sugar that was called dextrose. Dextrose is now recognized as just another name for D-glucose. This is D-fructose, and it's now recognized as allulose. It's just another name for D-fructose. D-fructose turns out to have a large negative rotation. Compared to D-glucose as the alpha and beta forms. It has a smaller positive rotation. And so when you get a 50-50 mixture of the two, the net result is negative rotation. The reason invert sugar is especially sweet is because D-glucose is actually one of the sweetest of all the monosaccharides. Invert sugar is used because it's cheaper, it gives more sweet taste than glucose itself does. Invert sugar is no longer used to any great extent because it's a cheaper way to get sweeter sugar cheaper. And that's this stuff called high fructose corn syrup. Just to give you a brief idea of how this stuff is made, basically you take cornstarch, starch from corn plants. That stuff's especially cheap, much, much cheaper than sucrose. It has almost no sweet taste. Remember, starch is a polymer of glucose. If you hydrolyze this, it can be done in plants with just acid, and you can add enzymes. It gives plus glucose. Plus glucose is cheap, but it's not especially sweet. So there's an enzyme that converts glucose into fructose and eventually reach equilibrium. Actually, the this is turned back into the carbonyl form and goes back to glucose. If this is turned into the carbonyl form, it goes to fructose. Mixture of the alpha and beta of both of these. When you do that, you get about 50% of each of these. Then it reaches equilibrium. It won't go any farther. But the net result is to turn very cheap cornstarch into a sweet tasting sugar, mostly because of the fructose. Whether this stuff is good for you or not, I don't know, but it behaves essentially the same as invert sugar. Those that sweeten do the same thing, at least at the high fructose concentration. Let's see, there's one more reaction left in this chapter. And that's the Kildani-Fisher sequence. This is a reaction that involves two steps. And the first step was discovered by a German chemist named Heinrich Kiliani. Then Emil Fischer took over the rest of it and applied it to sugars. It's basically taking things that aren't sugars, let's say any aldehyde. This is a reaction, you know. You can add hydrogen cyanide to an aldehyde, and cyanide acts as a nucleophile. Acts the carbonyl, it opens up, picks up a proton. And you may remember these things are called cyanohydrins. This is a cyanohydrin. This is the part that Kiliani discovered. And Fischer applied it to sugars. And he noticed that you can reduce the cyanide, if you're careful, with hydrogen and palladium, so that only 1 mole of hydrogen goes across the triple bond, meaning you get a double bond and the carbon. You can stop cleanly at this stage. And that is an imine. It's the sort of thing you get if you add ammonia to a carbonyl compound here. And you can make this go backwards, as you can with all amines. You just add water and acid. The nitrogen comes off as ammonia. Carbon-nitrogen double bond is replaced with a carbon-oxygen double bond. You get this idea. Mostly what you should have in your notes from way back in the chapter on aldehydes and ketones is that if you add ammonia to this, the ammonia will add to the nitrogen to give you, to the carbonyl group to give you the imine. All of these can be hydrolyzed with water and go backwards to whatever the amine is, or whatever the ammonia compound is, and this carbon-nitrogen bond becomes the carbonyl. If you apply this to sugars that are aldose sugars, this is what Fischer observed. I don't know whether he actually did it with glucose, but it's the easiest way to explain it. You call all of that the Kiliani-Fisher sequence. And you should be able to see that if you take glucose cyanide will make a cyanohydrin with the aldehyde at the top. We'll hydrolyze that cyanohydrin to an aldehyde. This carbon will have an OH on it, see below the aldehyde. One point I should have mentioned here, when you do this, that carbon becomes a chirality center, like that. And that's the carbon that was the carbonyl, which of course can't be a chirality center. That means that you get a mixture of R and S. The same thing happens when you do this on glucose. You get a mixture of R and S form. One carbon longer, which means instead of 4 chirality centers, you have 5. Aldehydes at the top. This is the new center that was the old carbonyl. Get this sugar. Same sugar except this OH is on the other side. All the other OHs are where they were in glucose. This amounts to its chain length of an alkane. That's the way it's described. It has one more carbon at the top, and then the old carbonyl, which is that carbon, becomes a chirality center. And you get either the R form, which has the OH on the right, or the S form. But note carefully that this, which is the same as this, is the same as it is in glucose. Nothing happens to this. Keep all of this constant. You add one more carbon at the top and put the OH on either side and get the two sugars. That's the way to think of the Kellogg-Fisher sequence. What's interesting about it, probably the only reason I mentioned it, this explains the origin of D and L nomenclature, the reason for calling this a D sugar. And the OH is on the other side, it's an L sugar. Related to the Kellogg-Fisher sequence. Let's just take an example. I need lots of room. Start down here. If we take the simplest of all sugars, has only one chirality center and just 3 carbons. That's called glyceraldehyde. It happens to rotate right positively, so it's called glyc plus glyceraldehyde. Fisher and could figure out anyhow that if you take this form plus glyceraldehyde, by the way, you should know there's no way of looking at this and telling it it's plus. It's very hard to determine even experimentally. A D sugar, which this is not the same thing as calling it a plus form. Some D sugars are positive, some of them are negative. There's no connection. Plus glyceraldehyde is D-glyceraldehyde, the way we name it. Because this OH is the bottommost chirality center. It's on the right. That's the pattern for D sugar. If you take plus glyceraldehyde, the plus form, 4 sugars. You'll get one sugar which has this at the bottom, 2 carbons, and another one that can be either on that side or this side. You get 2 sugars from this. 2 sugars that have this part the same, but this one they up here. Good drawing. One on the left, you take this plus this. Let's leave off the hydrogen. The one on the right, this one, you get 2 more sugars. Bottom 2 are the same, they get their own independent. Take this mixture and do a Kalani-Fisher sequence on it, you get a mixture of 4 sugars. Those 4 sugars are all possible. These sugars with 5 carbons. Like that. And what happens if you take this mixture? Don't separate them. It'd be very hard to separate them. The Kalani-Fisher sequence on the mixture. How many sugars will you get? 8. Each one of these will give 2. 2 for this, 2 for this, 2 for this, 2 for that. You get a mixture of 8 sugars. Those 8 sugars will be all possible. D, also hexoses. One of those 8 that will actually be D-glucose. Where will the D-glucose come from? It'll come from this sugar, which will add an OH over here on either side, and when the OH is on that side, it's D-glucose. Fisher was aware of this. Sometime in the 1880s, he set about to determine the structure of D-glucose. He was aware that he could get to do the structure of this, he would immediately know the structure of the bottommost chirality center in glucose. He was saying this. He figured there would never be any way you could tell the difference between here and here. You would never know for sure whether the OH was on this side or this side. All you could say for sure is that the OH is on this side. And if you do all these Kalani-Fisher sequences, he knew you got the glucose. If the OH were on the right in the plus form of isoaldehyde, it would have to be on the right in the glucose. From that, he could determine the other sugars. It took him 20 years, but eventually he did it. Fisher guessed that the plus form of isoaldehyde had the OH on the right. And he concluded ultimately the structure of glucose based on that. He figured no one would ever know whether he was right or wrong, because there was no chemical way you could tell the difference between the OH on this side or that side. That's true, but there are physical ways. In principle, you could magnify this stuff up large enough so that you could look at it and you could see what its structure is. That's more or less what X-ray crystallography does. It took half a century in 1951 X-ray crystal structures plus glyceraldehyde was D-glyceraldehyde indeed, and Fisher had guessed correctly. Show that plus glyceraldehyde is, as Fisher called it, D-glyceraldehyde. That's fortunate he was correct, because if he'd been wrong, all of the structures of chiral molecules that had been determined from about 1900 to 1951 had been based on his guess. The oil was on that side. If he guessed wrong, all the structures, including the structure of glucose, would have had to been replaced with a mirror image. And that was quite a few thousand different molecules and structures related to this. Where does D and L come in from this? Well, it's just this, is any sugar can be prepared by a series of Kalani Fisher sequences. On the plus form of glyceraldehyde, if you guess that the OH is on the right, as Fisher did, then it'll be a D sugar, if that's what you call it. And anything that should be made from minus glyceraldehyde the mirror image of plus glyceraldehyde. Fisher called an L sugar. That's the origin of the nomenclature D and L. If you didn't know this, it's kind of mysterious. Why bother to name one bottom chiral center that's D or L and ignore all the others? Because you can relate all of the D and L sugars to plus or minus glyceraldehyde by the Kalani Fisher sequences. All right. That's everything in this chapter on sugars. That you need to know. Which means we're on chapter 26. On amino acids and peptides. Peptides, of course, are the short proteins. We'll talk about that. There are just a few things you need to know. You need to know very briefly the nomenclature of alpha amino acids. Whether you say alpha amino acids is just amino acids, but you take it as the same thing. You need to know the synthesis and the resolution of amino acids in the lab. The synthesis we'll talk about is the amido-malonic ester synthesis. You need to know the Edmond method for determining peptide sequence. And then finally, we'll briefly look at the laboratory synthesis of peptides. And mostly what you They just differ in what this R group is. If that R equals hydrogen, that's the simplest of all amino acids. That's glycine. Amino acids are often given three-letter abbreviations. You should know the name of the simplest amino acid at least. And it's three-letter abbreviation, GLY. You probably know the next one too, and that's enough. If the R group is a methyl, replace one of the hydrogens in glycine with a methyl group. This is alanine. There are others that go beyond that. If you think of them in terms of an R group, it's easy. If it's an isopropyl group, it's called valine. If it's an isobutyl group, it's called leucine. The secondary butyl group is called isoleucine. Those are the only ones I know. These two, that should be enough. Others you can already look up. All of the alpha amino acids except glycine have a chirality center. That carbon, it's a chirality center, which means you can have R and S forms. These are usually named, Emil Fisher did it. It's still used. They're also named as D and L isomers. In more or less the same way that D and L is applied to sugars, except it makes more sense here because of the complete name when you specify D or L, because there's only one chirality center to decide that. It's done with Fisher projections. Definition is this is the parent chain in an amino acid. Put the parent chain on the vertical line of a Fisher projection. We're going to use UPAC, that's what I mean by the parent chain. And put carbon number 1 by the UPAC convention at the very top of that vertical chain. And an amino acid named by UPAC, that would always be number 1. Quicker way of saying it is put the carboxylic acid group at the top. Then, once you do that, you either have the NH2 on that side, or you have the NH2 on this side. And according to Fisher, we call this Al. This is an Al amino acid. If the NH2 is on the right side, it's a D amino acid. Modern day we would use RNS, but convention is these are still preserved. Al amino acids means that, and D amino acids means that. One point is that there are some 20 amino acids that occur in nature. Occur in living organisms, essentially. All are Al amino acids. That fact that all living organisms on our planet have the Al configuration of the amino acids is probably the single strongest argument for evolution responsible for everything on Earth, the living form. All right. That's enough on nomenclature. Let's go to synthesis. Laboratory synthesis of amino acids. We'll just look at one more. It's based on melodic ester synthesis, and you should recall this. You need it for the final. It kind of makes sense out of what we're learning. Remember, the melodic ester synthesis is the way it started with diethylmalate. Going through steps where you would add sodium oxide as a base, then add an organic halide, then hydrolyze, you get ethanol, carbon dioxide, and the thing you're interested in. Carboxylic acid that looks like that. And what's usually suggested is you think of this as a way of alkylating acetic acid. You look for a piece of acetic acid in the carboxylic acid you're trying to make. That R group tells you what organic halide to use. Like that. If you want to adapt this so that it makes an amino acid, just look at these and think about it for a while. You do the same sequence of steps. What you need to start with appears to be something like this. With an NH2 group there. Follow that sequence through with this molecule. Sodium oxide. Add an organic halide. Then hydrolyze. Should lose carbon dioxide. Two molecules of ethanol. And if everything works, you should measure. Instead of getting an alkylated acetic,